Out there, back to Boulder we go. So I'm excited to talk to you about new observations that we have of water vapor MPDs, which stand for Micropulse Differential Absorption lidars, and their impact on convective weather forecasting in an OSSI, or Observing System Simulation Experiment. Thank you so much to the organizers for letting me talk about this exciting work that we're doing at NCAR. I have several co-authors on this presentation, and we're all at NCAR. These include Jun Kyung Kei, Scott Spuler, Glenn Romine, and Jenny Sun. So first I'm going to tell you about the instrument, and then I'll tell you about the OSSI. So MPD stands for Micropulse Dial, and this has been developed through a really fruitful collaboration with Professor Kevin Rapasky at Montana State University, as well as the engineers in the Earth Observing Laboratory at NCAR. So let me break it apart into the different acronyms that we put together to create the name of MPD. First of all, MP stands for micropulse, and this is a class of laser remote sensors that use low energy or micro pulses of light at 5 microjoules at high repetition rates of 7,000 hertz, and we use photon counting receivers. The D stands for dial. It's an embedded acronym in there. This is a class of laser remote sensors that measure the difference in absorption between 2 nearby frequencies. And I'll show you a little bit more about that in the next slide. And then the lidar is for light detection and ranging, which is a type of active remote sensing that's similar to radar, but instead uses light in the form of a pulsed laser to measure the ranges. So I'd like to describe how the dial technique works. It's really slick and clever, powerful technique that gives excellent data quality. So I'm going to show you the dial technique that we're using for water vapor, but it's very similar for ozone as well, in that they both use 2 tunable wavelengths or frequencies that are very close to each other. For our water vapor MPD, we're using 828 nanometers. So if you look on the figure on the left, we're showing that we're transmitting an online frequency that's very close to a water vapor absorption peak, around 828 nanometers. And then we transmit an offline signal that is not absorbed by water vapor in the atmosphere. And we simply look at the ratio of the signal returned between the online and offline transmitted frequencies, and that gives us the range resolved water vapor number density or absolute humidity. So the advantages of this technique are that it's a direct measurement. There's no external calibration required for the narrow bandwidth frequencies that we're using, and it provides very high accuracy. The challenges are that it gives or requires very high spectral purity and fidelity of the laser transmitter. We have to be able to tune it exactly, and we have to know where it's tuned exactly to be able to make these precise measurements. But we've achieved this with relatively low cost and eye safety and low maintenance using commercial off-the-shelf parts. Here's an example of data that we've obtained from MPD from 2 different field campaigns. The top 2 panels show data from a pecan field campaign in Kansas in 2015. The bottom 2 panels show data from Argentina from the Relámpago field campaign in 2018. So for the top panel of each of these, I'm showing the relative backscatter from the surface up to 12 kilometers above ground level. So there's just a time series of these profiles from MPD with 5-minute temporal resolution. The second panel for each of these cases, or each of these field campaigns, shows the water vapor. And you can see lots of variability in the magnitude of the moisture as well as the depth of the moisture that's returns. So we're seeing lots of diurnal variation in the depth of the water vapor because the background solar radiation is really hard to filter out during the daytime, so we can't see as high up during the day as we do at night. But given that, we also have some gaps in the data when there's strong clouds. We can't see through optically thick clouds with the lidar. But you can see that the systems were just operating continuously. We have over 95% uptime from these both of these field campaigns. We just set it up and we tune it to the appropriate frequency, and then it just operates continuously in an unattended mode. You can see lots of variability in the magnitude and the depth of the moisture, and we're really excited about this new capability. We also did some validation work of the MPD and compared it with more mature instruments that are capable of measuring water vapor profiles. So these instruments were all co-located with MPD during a couple of field campaigns. The top left panel shows comparisons with radiosondes, and we see a correlation coefficient of 0.95. We're really happy to see that high agreement. But the radiosondes are just launched a couple times a day. We don't have continuous comparisons. And the top right panel shows us continual comparisons with an ARI. That's a passive remote sensing instrument that operates continuously, just like MPD. And there we see the correlation coefficient of 0.79. The comparisons are also good with profiling microwave radiometer, and also good comparisons with integrated precipitable water from ground-based GPS receivers. The panels on the bottom right are particularly interesting. They show a 24-hour time series comparison of MPD on top, ARI in the middle, and profiling microwave radiometer on the bottom. So they all three compare very well in water vapor depth and water vapor amount and variability. However, MPD is the only one that shows elevated moist and dry layers. The passive remote sensor retrieval capabilities just don't allow us to retrieve the information that illustrates an increase in moisture with height. So the active remote sensing capability of MPD is much preferred when there's changes from the standard decrease of water vapor with height. So we're using MPD to evaluate the precursors to convection initiation and to better understand water vapor variability and vertical variability of moisture. We're also using MPD to study the observation impact of assimilating water vapor profiles into NWP models to improve the forecast skill of high impact weather events. So this is one of those efforts that we're working on right now using an OSSI. This OSSI effort is based on a squall line that occurred on the 15th of July in 2015 during the Pecan field campaign. You can see the 2-hour evolution of this system becoming more organized as the MCS propagates across northern Kansas. This describes the OSSI experimental design. So what we're doing is we start by running a 40-member WRF, Weather Research and Forecasting Ensemble, to find the member that best represents reality. And then we call that the nature run. And that's shown in the lower left, second from the bottom left. And so that becomes our truth in this OSSI study because it most closely compares with the real observations that are shown in the upper left thumbprint. The worst member that performs the poorest, we're calling the control run. And then we're going to use that to assimilate simulated data. We're going to put simulated data into the control run to see if it improves the forecast to determine if it becomes more similar to the truth or the nature run. So you can see that the control run is pretty poor result. It hardly produces any precipitation at all. So in addition to the subjective comparison of these thumbnails, we can also use objective measures to compare the intensity, shape, location, and evolution of convection with the real observations in defining the nature run and the control run. So this describes the model setup. In the upper left, you can see that we're using WRF with a 15-kilometer outer domain and 3-kilometer inner domain with 70 vertical levels. You can see the physics schemes that we're using, and then the time series, the timeline in the center shows how our assimilation goes. So for the nature run and the control run, there's no assimilation at all. And then what we're going to do is 2 different DA experiments, 2 different data assimilation experiments as described in the bottom left. We're going to do a SOND Q. That's what we're calling this DA experiment, where we use simulated data from Raywin SOND and assimilate that into the control run. So we're using Raywin SOND wind, temperature, and pressure, and Raywin SOND moisture as well. And we're going to compare that with an MPDQ experiment, where we take the wind, temperature, and pressure from the Raywin SOND, but instead of the water vapor from Raywin SOND, we're using water vapor from the MPD profiles. So we're doing the simulation of that for a 3-hour period, and then running the forecast to see how they compare. So here's the results of the forecasts. The top row shows the observations. The second row shows the nature run, which is our truth. And the third row shows the poorly performing control run that we're trying to improve upon with the data assimilation. The fourth row shows the results of the data assimilation experiment using only the Raywin SOND data. You can see improvement over the control run for sure. However, if you look at the bottom row, where the MPDQ experiment using water vapor profiles from MPD, that produces the results that are most consistent with the nature run. The quantitative metrics also support this conclusion, which I'll show you one example of our quantitative metrics here. This is to compare the 1-hour accumulated precipitation fraction skill score. Here I'm showing the FSS for 2 different thresholds of 24 kilometers radius of influence for verification, and a rain rate of 0.5 millimeters per hour on the left and 5 millimeters per hour on the right. So the higher the FSS, the better the forecast skill. It's clear that the control run in gray just does a very poor job of the forecast, just as we expected. The green line showing the Raywin SOND assimilated data does better, much better than the control run. However, the MPDQ data assimilation experiment is better than all of the other forecasts. And this result also holds for nearly all rain rates, all radius of influences, and all forecast lead times. We looked at everything from 1 to 9 hours. So in summary, MPD is a tool we're really excited about. We can use it to accurately measure continuous profiles of water vapor. We currently have a network of 5 of them. Short-term forecasts of convection initiation, convective evolution, and precipitation of an MCS that occurred on the 15th of July in 2015 are improved by assimilating MPD profiling data in comparison to assimilating conventional surface and Raywin SOND observations. Assimilating MPD water vapor profiles increases the precipitation forecast skill over almost all forecast lead times and thresholds. And the improvement of the convective intensity and evolution forecasts we're attributing that to the correction of elevated moist air above or ahead of the MCS, which is possible due to our frequent updates of the MPD water vapor profiles with the high vertical resolution compared to Raywin SONDs. And our ongoing work includes adding wind and temperature profiles into this OSSI study, and also we're looking into assimilating MPD using real data sets that we've obtained from recent field campaigns. Thank you very much, and I'd be happy to answer any questions that you have.
Thank you, Tammy. That's very interesting. We have a question from Robert Rogers. He said this is an interesting approach to the OSSI, picking the best and the worst ensemble members. The question is there a risk of identical twin issues if you're using the same basic model configuration for your nature run and for your DA run?
Yeah, that's interesting. I think this is a little bit different formulation of an OSSI than a lot of other people have used, although there is some, there have been other researchers that have used the same way to create the nature run. So I think that what we're trying to do here is just to basically show the improvement to the forecast using various data sets. So by just looking at the difference within the same framework, I think it's a valid approach to assess which of these observational capabilities provides the best improvement to the forecast skill.
Right. I know we have two questions, one from Brian Golding and one anonymous, but for your runs, what was did you have just one MPD, or did you have more than one? Did you have a network of these systems?
Yeah, sorry, I didn't point that out. I had a picture of okay, so we're using 11 MPDs right there located in the inner domain. So we chose the sites of the radioson network in the central US and put the MPDs at the simulated MPDs at the same locations as those radioson sites shown there.
Okay. So I'll ask one question. Your very last point and your conclusion, you mentioned using adding UV and temperature. What would you get? Where would you get that data from? What other sensors would you add to this list? To the MPD?
Right. So we're thinking that we want to use wind profiles from either radar wind profilers or Doppler lidars, and temperature profiles. We can obtain those from potentially airy systems. These passive remote sensors that give us retrievals of temperature and water vapor both.
All right.
So this is just in the ASI framework. So we're just simulating these profiles and these capabilities using various data sets.
Right.
For number one, anyway.
Okay, that's great. It's one of those missing things that we've been looking for a long time. Water vapor. So thank you very much, Tammy.
Yeah, thank you.
Okay. So our next speaker